On page 641, we're going to talk about compositions of functions. Now, composition just means that you're going to, or compositions of transformations, sorry. Composition just means that we're going to do more than one transformation to our preimage. Okay? So we're going to draw compositions of transformations and then the usual, in a plane and in a coordinate plane. If we look on page 641, the first type of composition of transformation we're going to talk about is called a glide reflection. It says when a transformation is applied to a figure and then another transformation is applied to its image, the result is called a composition of transformations. A glide reflection is a very common type of composition of transformation. And it's a lot like the name sounds. A glide reflection is the composition of a translation, that's the glide, followed by a reflection. And the line of reflection is parallel to the translation vector. So, in other words, you translate the preimage, and then you reflect that, the resulting image gets reflected in a line of reflection that's parallel to the movement you just made with the translation. Okay? So, you glide it, then you reflect it. An example they give here is of these sets of footsteps here. So if you start with this foot and then you translate it up to here, reflect it across that line of reflection, translate it up to here, reflect it across that line of reflection, and so forth. Okay? Now, you can make as many different transformations as you want. Okay? You can just do one translation, one reflection. You can do translation, reflection, as many times as you want. Let's see how we can do. On page 645, let's take a look at number 1. Triangle CDE has vertices C, D, and E. Graph triangle CDE and its image after the indicated glide reflection. So go ahead and get out your graph paper, and let's graph this. Let's graph the triangle. So let's see here. -5. -5, -1, and go there. -2, -5 will be there. And -1, -1 will be there. Use your straight edge to connect the vertices. And there we have triangle CDE. So first we translate it along the vector 4, 0. Now remember what we do here. Let's write this with this notation. So that x coordinate of 4 means 4 to the right, which means we add 4 to each x coordinate. The y coordinate of 0 means 0 up or down, so we don't add or subtract anything from the y coordinate. So that means that C prime, we move it 4 to the right, 1, 2, 3, 4, and that's where C prime is. Then E prime will be 4 to the right, 1, 2, 3, 4, right there, and D prime 4 to the right, 1, 2, 3, 4, right there. Then we use our straight edge once more. And there's our translation of triangle CDE. But we're not finished. We've done that. Now we have to reflect this in the x-axis. Well, here's the x-axis. Okay, so maybe you remember the rule. It'd be nice, wouldn't it? That when you reflect in the x-axis, the x-coordinate stays the same, but the y-coordinate changes signs. Or you can just count spaces. Look at C prime. Since C prime is one space below the line of reflection, C double prime will go straight up one space above. So there's C double prime. E double prime will be one space above. But then D double prime, let's see, D prime is 1, 2, 3, 4, 5 spaces below. So D double prime goes straight up 1, 2, 3, 4, 5 spaces above. Then we use our straight edge one more time, and that, got to label D double prime, and that then is the result of that glide reflection. That's the result of our composition of transformation. We've talked before about how if you perform a translation or a reflection or a rotation, that the resulting image is congruent to the pre-image. Is our final result there, C double prime, D double prime, E double prime, congruent to the figure we started with? It is. It better be, hadn't it? Because all we did to it were rigid motions that do not change the size or shape of the original figure. Okay? So, any questions on doing that glide reflection? All right, let's try number 2. But let's try number 2 a little differently. Okay? Let's go ahead and start the same way. Let's graph this. So C is -5, -1 again. 1, 2, 3, 4, 5. There's C, and D was -2, -5, and E is -1, -1. So we start off the same way. We take our straight edge and we connect the vertices. All right, so there's triangle CDE to start off the problem again. But here's what I want to do differently. All right, instead of doing all this on our graph paper, I feel pretty confident I can figure out what the coordinates of my final figure are going to look like even without graphing it. Okay? And here's how I'm going to do it. First, I'm going to rewrite that translation vector as a function telling me what to do to my x and my y. So that would be the ordered pair xy becomes the ordered pair. What do I do to the x? Nothing. What do I do to the y? +6. Okay? So I can figure out the coordinates of C prime, D prime, and E prime without graphing it, can't I? So let's do that. So C prime, the x-coordinate stays the same, so it's -5. But for the y-coordinate, I add 6. So what's -1 + 6? 5. D prime, the x-coordinate stays the same. That's a -2. But for the y-coordinate, I add 6. So the new y-coordinate is 1. And for E prime, the x-coordinate stays the same. And what's the new y-coordinate? 5. Okay? I think that I know how to perform a reflection in the y-axis. Okay? And just for a moment, let's pretend that I've forgotten the rule. There's a rule for it. It was on your last quiz. Well, maybe it was the one in the x-axis. But anyway, you're supposed to know that. I'm going to get C double prime, D double prime, and E double prime. But let's, again, I've forgotten the rule. So I'm just going to make up a point. I'm going to put it right there. Then think, okay, if the y-axis is the line of reflection, that's there. All right, that's 2 to the right of the line of reflection. So its reflection would be 2 to the left. So the y-coordinate did not change, did it? And what happened to the x-coordinate? Multiply it by -1, change its sign. So to do the reflection, the ordered pair xy becomes the ordered pair -x, y, right? So even though I forgot the rule, I just remembered the rule. And now I know what to do to get these coordinates. So what's using our new function notation there, xy becomes -xy. What's the x-coordinate of double prime? 5. And what's the y-coordinate? Still 5. All right, d prime, what's the x-coordinate? Y-coordinate stays 1. And what then are the coordinates of e prime? And now I can graph that. Okay? And if I'm following the directions right, it says to graph triangle CDE, which I did, and its image after the indicated glide reflection. So I don't have to have that one on my graph to still follow the directions, do I? It's not wrong to have it on there because that's how I figured out where the resulting image was going to be. But I'm still following. Man, what did I do? I'm still following the directions. Where? Okay, I'm confused. Finally got the right place for the third time, right? All right, so let's graph this. So we'll have C double prime is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There's C double prime. D double prime is 1, 2, 1. There's it goes. And E double prime is 1, 5. Right there. Use your straight edge. And there we are. That last triangle is congruent to the first one. All right. You think you can do a glide reflection? You think you can do it either way? You should be able to. Do I care which way you do it? Nope. All right. The word isometry. Our standards use the 2 words rigid motion instead of isometry. An isometry is a transformation that results in a congruent figure. So the translations, the rotations, the reflections that we've been doing can all be called isometries. All right? And this theorem says that the composition of 2 or more isometries is an isometry. So if we have any combination of translations, reflections, and rotations, the resulting image, it doesn't matter how many of them we do. If we combine 2 of them, 3 of them, and then, or you start going around, you do a translation, then a reflection, then a translation, then a rotation, then a reflection, then a rotation, then a translation, then however many you do. Every time you do one, the image is congruent to the pre-image. So no matter how many of these transformations you put together as a composition of transformations, you will get a congruent figure every step of the way. That's what this theorem says. Okay? So, reflections, translations, rotations, and any combination thereof are called isometries, or they are called rigid motions, or they are called congruence transformations. All right. I think you've got that. I don't think we need to do another one. All right. Now this is kind of strange. When you do two reflections in a row, depending upon the relationship with your line of reflections, one of two things is going to happen. The composition of two reflections in parallel lines is the same as a translation. The theorem says this: the composition of two reflections in parallel lines can be described by a translation vector, or for us, writing it as function notation, that, and I don't really care that the translation vector is perpendicular to the two lines. I kind of care that it's twice the distance between the two lines. But here's what we really need to recognize. Look here, we're starting with this blue triangle over here that has point P as one of its vertices. Then we reflect it and get a green triangle, and you see that the point P is now point P prime over here. Then we reflect it again, and the line of reflection is parallel to our original line of reflection. And if you just ignored everything here in the middle and acted as if none of that was there, wouldn't you look at the blue figure and then the, what color is that? Last one. Brown figure. Wouldn't you just think that was a translation? So, the result of two reflections done with parallel lines is a translation. Everybody got that? The result of two reflections, or 3, or 50, done with parallel lines is a translation. Okay? Now, it does turn out that the direction that you went to translate that must be perpendicular to each of those lines of reflection. But I tend to think of that as a result more than a try to make it that way. Okay? But look what happens if your lines of reflection are not parallel. And if they're not parallel, they must be intersecting, right? Because we're in a plane, we're not switching planes. So if the lines of reflection are intersecting, look what's happening here. If you start with A over here, or the little blue segment, point A on it, you reflect it, you get this green segment with A prime on it, then you reflect it again, and you get this brown segment with A double prime on it. Well, you can't translate that blue segment to get the brown one, can you? Okay? So it's the same, though, as a rotation, isn't it? So two reflections in intersecting lines is the same result as a rotation. The composition of two reflections in intersecting lines can be described by a rotation about the point where the lines intersect, so we can even tell where the center of rotation is, through an angle that is twice the measure of the acute or right angle formed by the lines. So whatever the measure of that angle right there is, twice that is the angle of rotation. Okay? So here's what you need to know. When you perform two reflections, it will either be the same as a translation or a rotation. If the lines of reflection are parallel, it's translation. If the lines of reflection intersect, it's a rotation. That's what I expect you to be able to recognize. Questions? All right. So let's take a look at number 4 here on page 645. It says copy and reflect figure S and line M and then line P. And I'm going to mark that off of the directions. I'm going to mark off the word then and say, describe a single transformation that maps S onto S double prime. So our key is, are the lines of reflection parallel or are they intersecting? In number 4, our lines of reflection are parallel, so that doing two reflections with parallel lines is the same thing as translation. So all you write down, translation. Then we look at number 5. These lines of reflection are not parallel, they are intersecting. So instead of a translation, we get a number 6. Viviana is creating a pattern for the top of a table with tiles in the shape of isosceles triangles. Describe the transformation combination that was used to create the pattern. And for the most part, the simpler, the better, okay? You know, we don't want to say, well, what she did was she rotated it 360 degrees and then she, no. We keep it as simple as we can. So here's the way I see it. If I start with figure 1 right here, and I translate it right there, wouldn't I then get this? And then if I reflected that with that line of reflection, wouldn't I end up with figure 2? That's one way. What else could have been going on? It could be a rotation around that. What else could be going on? Then a translation. Whichever one you see first and it's actually correct, write it down. Okay? So like I said, what I saw, then a rotation. If you saw a rotation, write that down. If you saw reflection first, then a translation, down. But do just try to keep it as simple as you can. If you can describe it with 1 or 2 motions instead of 15, describe it with 1 or 2 motions instead of 15. You can put glide reflection, and you don't have to, then you've called it, our book considers that to be one thing. So yeah, you can do that, you can do that, and we're good. On page 640, glide reflections, the composition of a reflection and a translation. Translation is the same as the composition of 2 reflections in parallel lines. A rotation is the same as the composition of 2 reflections in intersecting lines. Any questions? All righty. On page 645, you need to do 1, 2, 3. For 4 and 5, just describe the transformation. Do 6 on 17 through 23. Just describe the transformation. 34, 35, 45 through 48.